Okay, so human activities kind of give us our year-to-year trend with regard to carbon dioxide in the atmosphere. Now, granted, this is a concentration in parts per million, which is lower, relatively low, but it's higher than parts per billion. Is that a homework for you that I see out? Oh. Thanks, sir. Yeah, go ahead and grab your homework while I'm thinking about it. On that? All right. Thank you. So one of the ways that we increase CO2 in our atmosphere is burning fossil fuels. You know, gasoline, oil, coal. That will automatically increase the carbon dioxide in our atmosphere. So we see that, they call it the hockey stick diagram. They're kind of like, oh, you see a little bit of noise, CO2 concentration. It runs about, what do we see, like max out about 300 parts per million. And then about the Industrial Revolution, it goes way up. So that's the hockey stick. So Industrial Revolution, we begin burning fossil fuels. Other ways that we actually are, and again, it's human activity when we change our plants that we have, and large plants, trees, and trees actually are good scrubbers. Trees take in carbon dioxide and spit back oxygen. So if we remove the trees, we kind of remove our ability to take out some of the carbon dioxide in our atmosphere. So we may wonder, well, carbon dioxide, we've heard global warming and all that. Actually, carbon dioxide has been part of Earth's atmosphere for a long time. And we need that little bit, we need things like carbon dioxide in our atmosphere to actually make us warm. So just making us warm is called the greenhouse effect. The other day, I put up Roy G. Biv, and I think I'm gonna, because we talked about Raleigh scattering, why our skies are blue, and I think I'm gonna do Roy G. Biv going backwards now. Just because I'm kind of used to putting the long wavelength here, the short wavelength here, a little bit farther, a little bit longer wavelength than red color, we have infrared, and then remember we have microwaves, and then we have radio waves. Okay, and this is increasing, the symbol for wavelength is this. Increasing wavelength and actually decreasing energy. And then over here, although we're not going to talk about this with greenhouse effect, we have on the other side of violet, we have ultraviolet, and then we have X-rays, and then we have gamma rays. Okay, so what happens is certain types of energy can make it through the Earth's atmosphere. So here we have the Earth's atmosphere. We're talking about, what was it, 60 miles thick or so it's not that thick. But the sunlight can come through the Earth. It actually then interacts with things on the Earth, including the Earth's surface. In this case, it comes through the glass of this greenhouse. It interacts with the inside of the greenhouse. This red squiggle mark then, so it enters here, sunlight enters, and it's converted to this. Infrared is heat, okay? So basically, then, it doesn't have the same, it can't get out. So visible light from the sun penetrates through the atmosphere, it warms the Earth, and then that outgoing heat or infrared radiation is blocked by carbon dioxide. I'll just kind of show you what that looks like. We say that carbon dioxide is selective. It basically ignores visible light, but it blocks or interacts with heat. So this is known as the atmosphere's greenhouse effect. And greenhouse effect, like I said, has been around for a long time. Sometimes the global warming is called enhanced greenhouse effect. Because as we increase carbon dioxide here in the atmosphere, we increase You can kind of already see where a little bit of this gets out, right? But if you have too much carbon dioxide, basically less and less of it gets out. Cool. Oh, video time. A greenhouse gas, but nitrogen and oxygen is not. Okay, so let's talk layers of the Earth's atmosphere. This will be consistent with what I put on the board the other day. And actually, it's kind of backwards, so I'm going to start with what's lowest to the Earth's surface here. So troposphere, when we look at the clouds, most clouds are in the troposphere. The troposphere is the most squished. It's not very deep, but it's packed full of gas particles. So even though it's the most shallow, it actually is the thickest. Troposphere contains the weather, and the troposphere is topped by the tropopause. And then going up, we have the stratosphere. Stratosphere is home to the good ozone. So there's good ozone and bad ozone. They both have the formula O3. The good ozone actually protects us from ultraviolet radiation coming from the sun. So I don't know if you guys have seen this or not, but several years ago, he's jumped twice, and his mom just has a heart attack each time, I'm sure. But let's take a look at this Red Bull jump. Did a cool job. So above the stratosphere, we have actually something called the stratopause. But the main layer after the stratosphere is the mesosphere, and then after the mesosphere, we have the thermosphere. And the thermosphere kind of what we say peters out into outer space. So the four main layers, or the first four I said, there's actually other kind of layers embedded in them, and those layers, and one of the layers is the ionosphere. Ion you might get from charged particles. So then actually part of the mesosphere and then on out to the thermosphere is this place that traps charged particles. And the charged particles that are trapped are actually originate from the sun in the solar wind, and they create, as they cascade through Earth's atmosphere, these things called northern lights. Northern lights near the North Pole, and southern lights near the South Pole. So on my bucket list is to do what I need to do. Ozone and bad ozone. So the formula for ozone, whether it's good or bad, is 3 oxygen atoms that are bonded together. If you have 2 oxygen atoms bond together, O2, that's normal oxygen in the air. So good ozone is in the stratosphere, and the stratosphere is the second layer of Earth's atmosphere. And what's good about the good ozone is that it protects us from ultraviolet radiation. I covering this topic in one of my other classes, and maybe you already know this, that actually there's a UVA, B, and C, and I might totally butcher this, but when you buy sunblock here on Earth, so here's the Earth, and here's the little person, and your parents would tell you, or you already know, to put on sunblock. And the sunblock, I think, covers A and B, okay? And the C is entirely blocked out by ozone. I think I got that right. It's actually blocked by ozone. By O3 in the stratosphere. But the good ozone in the stratosphere, actually it's a layer, so it's an ozone layer. We're concerned that it's been depleted by chlorofluorocarbons. Chlorofluorocarbons are CFCs. And so I kind of have a little bit to show you what that looks like. Yeah, the wiki kind of the depletion part. But before I go to kind of talk about the depletion part, I don't know if you can read this orange line up here, but this is a sign a few years ago that you might see on the interstate, and it's an ozone alert. And you're like, wait a minute, troposphere, stratosphere, good ozone in the stratosphere. Well, I'm going to do this. Here, my initials. Troposphere, I'll put a T for troposphere. Stratosphere, it's deeper, but not as thick. Then we have the mesosphere, then we have the thermosphere. So the good ozone is up here, good ozone layer. The bad ozone layer bad ozone is here. It's just from pollution. It's what we call a secondary pollutant. And so bad ozone, actually, if you have already breathing problems, bad ozone in the troposphere can be a bad thing. So this last little bit here talks a little bit about the ozone hole that you may have heard about before. One of the things I want you to know, and I have a student who actually has spent a fair bit of time in Alaska, one of the things you need to know is that the ozone hole is localized over the poles. We have an ozone hole over here, the North Pole, and ozone hole, the South Pole. And the reason it's over the poles is because it involves this special type of cloud. We talked about 6 types of clouds. One of them was not the polar stratospheric cloud. Right away, the whole thing that this type of cloud has the word stratosphere in it, you're like, wow. A cloud in the stratosphere? Yep, most clouds are in the troposphere. And only under really cold conditions can you get this special type of cloud. Anyway, if you read the story a little bit, what happens in the springtime in that hemisphere, whether it's at the North Pole or the South Pole, in the springtime these clouds start to break up. And the thing about these clouds, when they were in place, these little ice crystals actually would kind of tie up these CFCs, chlorofluorocarbons, which have a lifespan of about 100 years. Chlorofluorocarbons are banned worldwide now, but there was kind of a delay in about 100 years to get them to kind of go away. So when the CFCs are released, basically then they attack the ozone, and kind of all at once we have these holes that are created. So if you can kind of see these blue things over here, those are where it's blue is kind of where it's depleted. So actually this is showing a bigger hole. I might have had that right. Yeah, wrong anyway. Okay, the bigger of the 2 holes, so this is the southern hemisphere, this is the northern hemisphere. Oh, darn it. Okay, final answer. I can see Antarctica there. Antarctica. And in that case, if that's the case, we're talking southern hemisphere. Final answer. So in the southern hemisphere, the hole is more pronounced. I think this little video I have actually just takes you out to show you what those pretty clouds look like. Troposphere. Now, this over here, we've done a lot of figures in this class. Science does well with figures. Along this figure is a graph of, along the bottom axis, it kind of looks like it got cut off, is temperature. Let's see if I can bring that back. I don't know. And then along the y-axis is height. Maybe. I think I tried to bring it back before. I can't see that. There they are. Okay. That's better. So now you can see what I was talking about the temperatures along the bottom. I'll just make it smaller. So the temperatures over at the left are cold, and it increases to the right. So can you see where in the troposphere, as you climb a mountain, we know it gets colder. But check this out. After you go from the troposphere into the stratosphere, as in there, I think this is right, there are no mountains that extend beyond the troposphere. So you'd have to catch a ride with Felix Baumgartner. Then actually temperatures, as you go up in elevation, temperatures start to get warmer. The mesosphere temperatures start to get cooler, and the thermosphere temperatures start to get warmer again. Remember, thermosphere kind of peters into outer space. So we have this kind of alternating, and that's what the hidden words are. We have alternating cooler, and warmer. Now, granted, the whole warmer, as you go into outer space, it becomes a question of how warm is outer space. And it depends on how close you are to a star, or in our case, how close you are to the sun. Okay. So, one last topic with regard to our atmosphere is this idea of pressure. Now, air in general, we know it's mostly nitrogen, followed by oxygen, so kind of 80-20, 20% oxygen, 80% nitrogen, followed by argon. We have some variable gases. And one of the things about all gases is they create a pressure. And the reason gases create a pressure is associated with their motion. A few times up here, I've kind of put the, I'll do it one more time, at least anyway. I'll put my 3 boxes, and the first box will be a solid, the second box will be liquid, and then my favorite, the third box will be gases. And those gas particles are just, they have all this motion. And that's what we're talking about here. Of course, matter in its solid and liquid state also have motion, but they have a lot of motion, a lot of kinetic energy. So here's kind of a diagram of a parcel of air, and the little green ones are nitrogen. They're in far abundance. Then the little 2 red ones are oxygen. Then we have cute little water vapor. Okay, and they are all in here ramming around this chunk of air and creating a pressure against, I kind of figure it, pressure against a force against whatever they run into. Okay. So pressure in general is force divided by the area over which the force is applied. You've probably heard of PSI when you when you put air in your tire, you go to a certain PSI, whether it's 65 or 35. Okay, so that's the force, that's the pounds per square inch that the little gas particles in your tire are exerting. Well, we have to, in order to understand weather, because we're kind of building up to weather or understand our atmosphere, we need to understand the pressure that the gas particles are exerting on us. In general, we're running about 14 pounds per square inch, the gas particles, the nitrogen, oxygen, and water vapor. Okay, that's just how it is. So pounds per square inch is an important way of talking about pressure. Another important way of talking about pressure is actually millimeters of mercury or inches of mercury. So what does that look like? Well, of course, we know mercury is on the periodic table. It's Hg. The reason it's blue on the periodic table is it's one of the only 2 liquids. We got bromine and mercury under normal earth temperatures and pressures are liquid. So what happens is we put this liquid, we have this liquid mercury here that actually can shove liquid up this tube. This tube is closed up there. So as the pressure of the gas particles in the air increase, it has more force against the pan, which shoves more liquid up. So when we talk about inches of mercury or millimeters of mercury, we're talking about the distance that the liquid is shoved up. Typical pressure of the atmosphere in terms of inches of mercury would be 29.9 inches of mercury. So when we start looking at more surface maps, the pressure is not going to be in pounds per square inch. The pressure of the atmosphere won't necessarily be in inches of mercury. Usually it will be in MB or millibars. A normal or a typical pressure of the atmosphere, you're looking at 1,007 millibars. The abbreviation for millibars is MB. So let's see, I think this will work. When we talk about gases, one of the things that is challenging is you can't see the gas. So a lot of times we just confine the gas and then talk about it. So what this is, it's just a free moving plunger. And what I want to do is talk about the gas that's contained in this syringe, kind of inverted syringe. And it's just got a place on the bottom where I can go ahead and cap it off. So now when I assemble it, basically when I put the lid on, I have captured gas right there. So the way this works then, or can work, is right now that's probably about 14 pounds per square inch. But if I go ahead and put something on top of here, I think I'll put a couple on so it'll go down a little bit. Go down. So actually, how far this up here, this pressure that's being exerted actually is directly reflected in the pressure of the gas as it holds up the syringe. So what would happen if I don't think I can. I think I can. What would happen if I go ahead and pull that right there? They will all escape. And actually, that's one of the things we're going to hit in the next part. I don't think I can. I can step over. I had another desk. But anyway. Okay. So the opposite of this would be kind of lower pressure. And actually, as we climb a mountain, we get less and less pressure. The little bit of tinge of blue here is trying to show you that we have a lot, it's more concentrated, the gas particles are more concentrated here and less concentrated up there. So not Baumgartner, but there's Captain Kittinger, where he jumped from. So the greater the density of the gas, the higher the pressure. Density and pressure of the atmosphere get less or decrease going up, increasing elevation. So one of the things you're going to want to kind of make sure we're on the same page of is you climb a mountain, you are increasing your elevation. And the air gets thinner, the pressure decreases, the density decreases. In other words, as you climb a mountain, the air gets thinner and the pressure is less. Whenever you have a change, in this case a change in pressure, we call that a gradient. You might have heard of the word gradient before in like grade, if you're a truck driver, they will tell you like the percent grade, like this is 0%, this would be 3%, 45%. They talk about the change in elevation, okay, so gradient. I'm going to go ahead and get you kind of thinking about what we're going to talk about next. I'm going to put an H here, and H on a weather map, you guys told me stands for high pressure. I'm going to put an L here, okay, for low pressure. So the word is vertical. We have an ongoing vertical pressure gradient. All a gradient means is there's a difference between two locations. In this case, a difference vertically with regard to pressure. Great. So these will be due on Wednesday. Now, if you go to the front page, you want to take that where it says Part 4, cross it out and put Part 3 instead. Because otherwise you have Part 1, Part 2, and 2 Part 4s. So that should really be Part 3. And then this is the real Part 4. Yes. So, change that. All right. So it looks like I've got something in the textbook, and then I've also got 3 follow-up questions. So describe how gases create pressure. How does the density and pressure of Earth's atmosphere change as you go upward? Sound like good test questions. What's that? Oh, well, you definitely didn't. Just got sidetracked. Thanks for saying something. All right. Cool. That isn't what I thought it was going to be. Okay. You guys are right here. All right, that looks better. All right. So a few slides ago, you guys wrote in the word vertical, right? Now, to me, horizontal is the opposite of the word vertical. And I have to concentrate, just like I have to concentrate my left and right, I have to concentrate on vertical and horizontal, okay? Horizontal. I want to explain wind, and in order to explain wind is basically, wind only happens if you have a high and a low pressure. That's the only way wind happens, okay? So speaking horizontally now, we talked about air masses, and it's not as big as an air mass, so I don't want you to think like, because air mass is like the size of like Missouri. But think now kind of a smaller chunk of air sitting side by side, okay? And they have different pressures, and we'll talk about why they would have different pressures. Why would they have different pressures? Well, one of them is temperature. And one of the things about physical science is you're like, oh, that makes sense. So right here, I've got two columns of air. The red one is warmer, and the blue one is cooler. And actually, they have little words up here: warm chunk of air, cool chunk of air. A warm chunk of air, the little particles are moving faster, so they're fluffier. So I want to kind of talk about this region here, which would be close to the Earth. And this would be going up a mountain. This is close to the Earth. So can you see where actually this right here, for this warm chunk of air, it looks less dense? Relatively speaking, I'm going to put a letter L here. This is low. I'm going to put a letter H here, because don't they look close together? They're less movement. They're more squished together. This is a higher pressure, and that's a lower pressure at the Earth's surface anyway. So I'll show you what I want to do. So this is cold, cold, hot. This is the Earth's surface. And here I have a relatively low pressure and have a relatively high pressure. That works. Another one, and this is kind of counterintuitive. If I were at a muggy day in the summer, if I were to ask you, like, how's the pressure for you? Like, oh man, I just feel like there's a lot of pressure. But as it turns out, the more moist air actually has a lower pressure. So already then, like if you have at the surface, if you have a relatively moist chunk of air, it's going to be a low, and if you have a dry chunk of air, it's going to be a high. And this kind of says why that would be. It kind of comes down to weight. Your moist, your H2O molecules, they weigh relatively light, and so it ends up being a low pressure. The last one, I kind of think of, do you remember we had a picture of Florida? Here's my picture of Florida, goodness gracious. And we said that we have the Gulf here, Atlantic here, and kind of if you have air coming from the oceans, as it comes from the Gulf or the oceans onto land, it squishes up, kind of piled up. And we actually call that convergence too. This is sort of a different type of convergence. This one, oh, now I remember. Let's see, moving air converging is the word there. I kind of liken it to if you are on a playground with little kids and you have a bucket of candy, that's a dangerous thing. and you throw your bucket out, you're going to have little kids converge. And they're going to create, wherever they come, kid-wise, you are at a high pressure. So that's why I'm going to put the letter H here. We're at a high pressure here. You can almost see it. And then, I know how this goes. And then take that analogy a little bit further. So you have one kid that gets there and just like eats way too much. And that kid throws up. Guess what's going to happen? Everybody's going to leave. And you're going to end up with a low pressure. Okay. So those are kind of 3 ways that you can get pressure differences. I don't have it with me here today, but this is that's similar to that silver thing I brought the other day. And it's a true adage, and I mentioned the other day that there's all sorts of, I mentioned the word adage, there's all sorts of like little wives' tales that are true about changing pressure. Basically, if your pressure is rising, you can expect clear skies. And so when I brought in that dial the other day, that silver thing, this is over here. If you have falling pressures, okay, over here you're going to see precipitation or clouds anyway. And then if you have steady pressures, whatever you've got, it's just going to kind of stay where it is. I'm going to go ahead and circle these arrows. The up arrow means rising, the down arrow means falling, the arrow that's horizontal means it's steady. These are a lot of times what you'll see on the weather stations. They'll go ahead and just have an arrow. Okay, so Thursday's lab, what I'm thinking, I haven't decided for sure, but you guys are going to make these maps of sorts. I think I'll probably take us out to the internet and look at them. But, right, so if you've ever done much with like topography, like a topography of like a map of the United States, it will tell you kind of elevation. So, I have terrible dry maps of the United States. But we kind of have a couple mountain ranges, an older mountain range on our east and a newer mountain range on our west coast. So here is Florida. Okay. But to me, that's what that looks like. I would draw, where it's high, I would draw kind of these long things. These could be the Appalachian Mountains. These could be the Rocky Mountains. Okay, and then from there, this little one right here would be a high elevation. Okay, and then I would step down from that. I don't know if this is making sense, but this is to me what it looks like. I would step down, that's getting a little lower, and then I would kind of step down even further. Okay, and so you end up with these lines that connect the same elevation. That's exactly what this weather map is. You see these lines, but instead of elevation, and I kind of mentioned that we're going with millibars, they actually are telling you millibars. So you see where this is a low pressure, it's not a mountain, it's like a depth, deep. All these locations are 996 millibars. All these locations stepping up, 1,000 millibars. All these locations are 1,004. All these locations are 1,008, 1,012, 1,016. So it's very similar. So you need to fill in. So we see an H and an L. H marks the high pressure, central high, and L marks a central low. So these are contour lines with regard to elevation. These are contour lines with regard to pressure. Okay, the same pressure. Oops. And a lot of times it has this kind of bullseye look around it. Although the high bullseye looks blobbier and the low bullseye looks kind of tighter. The word is bullseye. think we're going to run out of time. This is an important part of this, to create wind. But can you see where these around the low are nice and tight, and around the high, they're blobby? Kind of like, go back to our elevation map. If I were to draw a lot of, if you've studied these very much, you'll be like, wow. If I were to draw a lot of lines close together, that means I'm looking at a hill, okay? If I draw them kind of far, that means it doesn't change very much. Okay, oh, sorry, we'll go ahead and do that one, and then we'll call it fits. So the closer the isobars, the greater the change in pressure, not going very far. Okay, that's it. So I'll bring my wind things on Wednesday and do it again.